Can it be in anything? Like a homework too?
Yeah.
Number 57, when you're adding the total capacitance, why do you add do you add them because they're for CP portion of that?
Well, said problem 57, this is page 766,
Yeah.
or from chapter 19.
Yes.
Find the total capacitance of the combination. So what was your question?
But why do you have to add 10 and 2.5 together? Is it because they're in series, that series or parallel?
Because they're in parallel.
Okay.
And you have to do those first because there's a junction between the 10 and the 0.3 and the 2.5 and the 0.3.
Okay.
Is that sufficient, or I mean, did you want me to go into
No, that's
excruciating detail?
No, that should be good. And then why is there 2 CPs in on the denominator and the numerator when you're solving for it?
Oh, let's actually just go through it. So it's 10, 2.5, and 0.3.
Yeah.
And 2.5 and 0.3. These are all microfarads. Just can't get the right angle now. All right, so first off, whenever you're doing the equivalent capacitance, you need to do what you can. You either do in series first or parallel first or both simultaneously, whatever's available. These right here are in parallel because they have a junction on both sides of them and there's nothing else in between. So current comes in here, it's gonna come out here, and it's either gonna go one path or the other. More officially, for things in parallel, the potential difference between these two spots is the same, and that will go into far more detail in the next chapter. So they're in parallel, and so you just add them straight up. So this is the equivalent of having a 12.5 microfarad capacitor and a 0.3 microfarad capacitor. And now we have a series circuit. And so when doing series, you add the reciprocals, 1 over 12.5 plus 1 over 0.3, and that's 1 over the equivalent capacitance. So you do the fancy math here, so that would be, I guess, 10/3, and 2 over 25. So common denominator is 75, so this is 6 plus 250 over 75, 256 over 75. And that's the reciprocal of the equivalent capacitance. So we have to take the reciprocal one more time. So that's equal to 256 over 75. And so the equivalent capacitance would be 75 over 256 microfarads. If you're using a calculator, it would obviously be some decimal.
Using the calculator, I got 75 over 31 microfarads.
You got 75 over 31?
Yeah.
Adding in the series reduces the capacitance. So it's got to be less than 0.3, whatever it is.
No, I got 256 over 75.
With,
Yeah.
okay.
Add a 3 to 0.3.
Ah, that'll do it. Was your question answered and more?
Yes, sir. Yeah.
Oh, there's the right angle.
Where did the 2 over 25 and 10 over 3 come from?
I just put these in fractions where I had integers to deal with. So this is 0.3 is 3/10, so that's 1 over 3/10. which is 10/3, and 12.5. 1 over 12.5 is 1 over 25 halves, which is 2/25. Any other questions?
Can we go to number 71? Or 61?
Okay, good, because I don't have a 71 here. $61, you said?
Yes.
All right.
I didn't got a different answer, but I probably don't.
Any other questions on 57 before I erase?
Can I take a picture?
All right, so 61, obviously a more complex system here. We've got capacitance right there, and then it splits off into, got one here, and it meets up again. And then on this side, I've got one here, and then this one splits off. And so these aren't microfarads. I'm just not going to bother writing units. So 5, 3.5, 8, 1.5, 0.75, and 15. Again, let's first identify the junctions. Junctions are where the wires meet, so I got here, 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 and here. So if I'm traveling from one junction to another junction down one of the paths and I cross more than one capacitor, well, that's series. So for instance, if I'm going down this path right here, from this junction to this junction through this path, I cross through these. In other words, any current flowing across one capacitor has to be the same current flowing across the other capacitor. And so that is series right here. That's it for the series and the first take on it. Over here, we have two junctions here, and we have two paths. Either path, we have a capacitor, so this is parallel right here.
Can you say that one more time?
Going from this junction to this junction, we have two different paths that we can take. Through either path, we cross only one capacitor, and so they are in parallel. And that's all we can do for the first round of simplification. So parallel capacitors are the easy ones to do. We just add them straight up. I can do that one without a calculator. And so we've got our 8 there in the middle. And then over this side, we have our 1.5. And then that blends into this parallel structure, which is a 15.75. And then over on the other side, we have the series. We're going to reduce that to a single capacitance, but we have to do the fancy math here. So this one, so 1 over this equivalent capacitance is 1 over 5 plus 1 over 3.5. And then with the calculator, just hitting a few buttons or doing board work. Let's see, that's 7 halves, so this would be plus 2/7. So that'd be 17/35. Or the equivalent capacitance is 35/17. So 2 and a little bit. Now I'm doing it in fractions just because it's easier up here on the board without a calculator. I'm not requiring you to do that.
It's not what I got on the calculator.
Whatever we get, it better be less than 3.5.
I got 0.485.
Did you do the reciprocal at the end?
No.
Because remember, when I add up the reciprocals, that's the reciprocal of the equivalent capacitance.
Okay.
So the two most common mistakes I see people make is getting to the reciprocal at the end and getting parallel series backwards with capacitors. And probably the third most common mistake is fat fingers on a calculator. All right, so now our junctions, we have two junctions here. I know that these two are in parallel. These two are in series, so I have a series circuit here. I have parallel here. Now I could do the parallel and do the series and then do another parallel, or in this particular case, I'm just going to do the series first. I'm not going to do the parallel yet, and then I'll have three in parallel, and we'll just do all those at one time. So my series here, I have 1 over my equivalent capacitance on this side is 1 over 1.5 plus 1 over 15.75. And whatever we get, we better get something less than 1.5. And I suspect it's just going to be a tad shy of that, so like 1.3. For the equivalent.
1.3695.
3695.
Which in fraction form is 63/46.
So now, our equivalence here is we've got our 8 in the middle. That still hasn't changed, that lonely 8. Then we've got this 35/17 over here. And then on the right side, we have our 63/46. I now have 3 in parallel, and I can just add them straight up. So whatever. So my final equivalent capacitance, 35/17 plus 8 plus 63/46.
11.43.
And then make sure we have units at the end, like the farads.
Do you want it in fraction form?
Sure.
8,937 780 seconds. Microfarads.
Just in case you're having a bad morning and couldn't do that in your head. Questions on this masterpiece of physics? All right. Any other questions?
This is still chapter 19, right?
Yeah, this is 19. When we're done with questions, we're gonna jump back into 20. Sarah?
So if you can add like more than 2 when they're in parallel, can you do the same thing when they're in series?
Yes.
Okay.
So if I have 3 in series, C1, C2, C3, then 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. Any questions before we talk about neat junk like current and resistance? So, some people are still scribbling down, so it's oh. All right. All right, back to chapter 20. So when Ben Franklin was first just dealing with this stuff, he always pictured electricity that was flowing through lightning and whatever as a fluid flowing, and so thus he used the term current, and that is what we're still stuck with. It wasn't until 200 years later we realized it was particles and not a fluid. Now the symbol for current, as you would expect, is an I. Obviously, yeah. More specifically, a capital I is DC current, which is what we're doing right now. We don't get AC till a little bit later. When we get to AC current, capital I will represent a maximum amount, and lowercase I, or the lowercase I, will represent an instantaneous amount, since current is constantly flowing, changing values. By definition, when you're doing current, it's how much we have charge. Charge passes by a certain point. It's the rate at which charge passes by a point, or math-wise, delta Q over delta T. This delta Q is less of a change in current in some structure, but more of how much current is passing by a particular point. So, how much charge passing by a certain point per unit time. And probably my best, almost legible writing. Therefore, let's just do a quick and dirty example here. So I have a wire here. And let's say every 15 seconds, I notice we have 5 times 10 to the 10th electrons passing by, going this way. What is the current? Well, first off, I don't have a charge yet, but I do have a number of electrons that are passing by. And so we have to figure out what the charge is. So what is the charge of 5 times 10 to the 10th electrons? Or how would you find it? What do you need to know?
Charge of an electron.
Yes, all right. So the charge of an electron is negative E, which is not particularly helpful if you don't know what little e is. What is little e? What is the charge of an electron?
6 to the -19.
Spirit of what you said, yes. 1.6 times 10 to the -19.
Coulombs.
All right, so the total charge here is 5 times 10 to the 10th electrons times 1.6 times 10 to the -19th coulombs per electron. The electrons cancel out, and what we're left with is, the fancy math, that would be 8 times 10 to the -9th coulombs, otherwise known as 8 nanocoulombs. And so I have 8 nanocoulombs of charge passing by every 15 seconds, and so now we just do the fancy division here. So the current, 8 nanocoulombs, let's go ahead and do times 10 to the -9th, times 10 to the -9th coulombs over 15 seconds. It'll be something times 10 to the -10th. 8 over 15. So it'll be 5.13. 33. Units?
Coulombs per
Coulomb per
second.
second.
Now, coulombs per second is perfectly correct. However, that was too much for physicists or engineers to write, so they came up with something different. That's 5.33 times 10 to the -10th amperes. So we have 1 ampere equals 1, by definition, 1 coulomb per second. Actually, I think officially 1 coulomb is 1 ampere second, but considering the order in which we're doing this, I'm defining amperes. And named after,
Pierre.
I think Anna was closer. Except there's an accent mark on there somewhere, so it's like ampere. My French pronunciation is as good as it's always been. Questions to hear? So we'll keep that up there. Really don't need that at the moment. I'm gonna keep my absolutely spectacular drawing up here. And I'll erase that in a moment. All right, so when we're talking about these charges, these electrons passing by, they're not going through there in almost every case. The electron really is coming in, it's hitting something and then bounces, and then hits something else and bounces, and then hits something, then starts. There's a slow drifting in this direction since there are electrons. This is the low potential, this is the high potential. The negative and plus indicating that it's as low and high, not indicating it's necessarily negative potential and positive potential. Or we can do it from an electric field point of view. Electric field goes from positive to negative, so I have an electric field going this way. Or somewhere over here, I've got this giant reservoir of negative charge, or over here I have this giant reservoir of positive charge, and it's being repelled by the negative and attracted to the positive. But the electron is moving back and forth here with a general drift going off to the right. And how fast it's going off to the right is called the drift speed, v sub d. So what I'm concerned with here is, can we quantify this a little bit better? Could we come up with some formula that would describe this motion, this relationship between, oh, let's say the difference in the potential and the current? Yes, we can. Now, I will be referring to my notes as I'm doing this just because there's a bunch of letters here and I really don't want to get a halfway into it and suddenly realize, oh, I made a mistake. So first off, the amount of charge that's passing by in a particular amount of time. So let's say we have a certain amount of time, t, and we're looking at the charge that passes through. So the charge that's passing through is going to equal to this letter n times the volume. So this would be the number of electrons, number of mobile charge carriers officially. Mobile charge carriers, which for probably almost everything that you will ever do in your life will be electrons, times the charge of an electron. I am, actually let's times Q. Let's keep it slightly generic. We'll put in specifics for electrons in a moment. This N here is the mobile charge carrier density, which is the number of charges per unit volume. This volume is, please do note the difference. Volume, I put the serifs at the top, and potential, I do not. So this V right here is a volume. This V right here is potential. So I have these mobile charge carriers that are moving along and so if they travel through some distance x here within the time delta t, And I have some cross-sectional area here of this, so this has some cross-sectional area. Then the volume we're talking about here is just, well, the cross-sectional area times the length, or x, as I have it listed there. So this becomes in a, I guess technically we'll make it delta x, keeping track with my notes there, delta x times whatever the charge is of the carrier. Now, the drift speed is a speed. It's distance over time. I'm not concerned with how fast this electron is traveling between bumping into things. I'm concerned with, how far does it actually travel in a certain amount of time. So it's just delta x over delta t. So delta x, therefore, would be Vd delta t. So I can make that substitution here. So the amount of charge that's passing through is in a, now I'm substituting in Vd delta t times q. If I divide both sides by time, then on the left-hand side, I have current. And on the right-hand side, I have in a VdQ. It's a subscript d. Now, obviously, I haven't brought in the electric potential yet, but at least I have some expression of current. So let's hone in, flash back to first semester course. Hone in and see if we can nail down this drift speed. So recognize this thing is, the electron's coming in, it bounces into something, bounces back, repelled, however you want to, depends on how fine-tuned you want to do the language there, but it's basically moving back and forth and slowly moving off to the left, or right, as you kids say nowadays. On average, though, every time it hits something, it's stopping. And as it stops, it then has to basically pick up acceleration again and start moving again. And so, how fast it's going is basically the acceleration times time. And the acceleration, well, that's the force divided by mass times time. This is the force on the electron divided by the mass of the electron. Or mass of the charge carrier. And the force, well, it depends upon the electric field. That's just going to be equal to the charge times the electric field over the mass. And so now, if we make that substitution, we have NA times QE. Let's see if I can actually draw letters today. QE over M delta T. What's the Q? I do need to make one change here. This delta T, I've got two different delta T's, and so I'm going to get rid of this delta T right here. This time right here is the average time it takes between colliding into things. It's not the same as this delta T over here. This delta T is how long, we're just timing how long it's, seeing how far it goes within a certain amount of time. This time over here is the time in between crashes, and so the symbol used is a tau. This is known as the, I'll say mean free path. I'm pretty sure that's it. I don't have it written down right here. So, but it's immortalized on video, so my mistake will be there forever.
Are the videos on your YouTube channel, or where are they?
If you go to Blackboard under course documents, you'll see links. And it's on the YouTube channel I do for this, so. Subscribe, maybe I can get up to 10 people subscribed. Then the money's gonna start rolling in. I wonder how the school would feel if I started doing ads. I think,
You have to have like a minimum of so many views to like monetize or something.
100 views? Can I do 100?
More than that.
Okay. All right, 100,000, so, you know, at some point.
I'm gonna tell you eventually.
You can do it.
Maybe if you titled your videos,
So I what?
title them,
Physics
Oh.
rules.
yeah, that when anybody searches something, they might, you might pop up.
Explosion.
I'm just trying to think of what would have to have been warped in my life in order for me to want to do that. Anyway. So this is a tau here, and tau here. Apologies for that. All right, so we can now combine this stuff. So we have this n q squared. Let's see, I want to keep a and e separate here over m tau a e. Now let's just be specific. I kept this as mobile charge carrier density. We can have protons moving. It is possible to get protons moving. This is basically high energy physics, where you take hydrogen atoms, expose it to a strong enough electric field, you'll rip the electrons from the protons, and so now you have a collection of protons which you can then shoot through a tube, and you have current. However, that's not usual life. So let's just go ahead and assume the mobile charge carriers are the electrons. So n e squared over the mass of the electron, tau a e. Recognize what we have up front, this part right here. Mass of the electron is pretty well constant. Good enough for what we're doing. Charge of an electron is pretty well constant. Then we're left with these two other things, this n and tau. These are dependent upon the material. The number of mobile charge carriers, the number of electrons that can move freely between atoms or through the electron sea, the number of charges that are free to move depends upon the material. And the time it takes between crashes depends upon how tightly packed it is, and that's also material dependent. So this whole thing here is just material dependent items and constants. So this